Hello and welcome to the video for 3.5. Alright, now so in this section what we're going to do is we're going to basically take the conversation we had in the first half of 3.4, you know, those library of functions, those basic graphs, and we're going to apply ideas of shifting, techniques of transformation to create new equations based on those general graphs, if you will. So just as a reminder, right, we are going to use those basic shapes, right, those known shapes, the library functions in 3.4. So just real quick, right, here was our shape of the square root function. We have the square, the absolute value, the cube root, the cube function, the reciprocal. These are really the six we're going to use in this section. As I mentioned in the 3.4 video, we've already graphed lines in great detail before, so we're not really going to deal with that here in 3.5. Okay. So first, let's talk about what would happen if we add or subtract a number to an equation. So for example, suppose we have the graph y equals x squared, and we want to obtain the graph of x squared plus 3. Right? So let's do a little bit of kind of exploration first. So let's think about numerically speaking. So if I look at some table of values of x squared, and then I look at a table of values of x squared plus 3, right? Look at basically what we're dealing with here. So if I plug negative 2 into the original function, again, negative 2 squared, which is 4, and then this is going to add 3 to it, which makes it 7. And if I plug negative 1 into the original graph, I get 1, and then I add 3 to that, and it becomes 4. And so on and so forth. So literally every y value is being moved up 3 units visually. I'm adding 3 to the original y value. Right? So graphically speaking, right, every y value is being moved up 3 units. I'm adding 3 to it. So if this black graph is the original square function, here's me adding 3 to every point on the graph. Adding 3 to every point on the graph, adding 3 to every point on the graph. And we're going to call this as a vertical shift. We've shifted upwards, right, in a vertical direction. And in a really similar fashion, if I take the same graph, the parabola, right, the square function, and I subtract 4, I'm going to basically be taking every y value and reducing it by 4. So if we look at a table of values, right, when x is negative 2, my original has a value of 4, and then I'm going to subtract 4 from that and get 0. And my original y value at x equals negative 1 is positive 1, and then I subtract 4 and get negative 3. So every y value is being moved down 4 units. So here's a vertical shift downward. All right, so here's my original square function, the black graph, and this graph is being shifted down 4 units. Now what we want to be able to do is generalize this idea. The idea is that whenever I add or subtract a number outside the function, outside the square function, that's a vertical shift. Right? So again, you know, just kind of a summary of a couple examples here. Let's look at x squared, let's look at x squared plus 2, let's look at x squared minus 2. And if we were to take out our calculator and graph those 3 equations, I would see this idea, right? Here's the original x squared, here's x squared plus 2, moved up to, here's x squared minus 2. So it's the same shape graph, I'm just shifting vertically. So what the book does, right, this is pretty standard in any algebra textbook, we're going to generalize this idea. We're going to say if a positive number k is added to the right side of the function f of x, then the equation that we now have, the new equation, is f of x plus k. And this graph is shifted vertically up k units. Now if I subtract k, then I'm going to be shifting vertically down k units, right? So again, I want to be able to generalize here. Ultimately, I don't want to use my technology, right? I want to be able to say, hey, sketch a rough graph of x squared plus 5, and you're going to know, oh, that's the basic parabola. I'm going to shift it up 5 units. All right, so this is the general idea. Remember, we talked about in the last section, we're developing our tools of analysis and quantitative reasoning. Even though we do have graphing technology to graph all these equations for us, we want to be able to do these things without that technology. We want to be able to develop our tools of analysis, right? But anyway, let's take this idea to a similar but different concept. So here, notice what I'm doing with this equation is I'm subtracting 2 inside the square function. This is not outside the square function, right? I'm not subtracting 2 outside the square. I'm subtracting 2 inside the square. So If we plot some points, this is really interesting. What we end up noticing visually is we have shifted the graph to the right 2 units. And probably the easiest place to see that is in the x-intercept. Right? So for example, x equals 0 would make y equals 0 here. X equals 2 would make y equals 0. So I'm taking that original x-intercept and I'm moving it over 2 units when I subtract 2 inside the square function. So this is a horizontal shift. We moved it to the right 2 units. All right, now let's add 4 inside the equation, right? So if I add 4 inside the equation and we plot some points, right, again, I think the x-intercept is the easiest one to look at. If I plug x equals 0 into here, I get y equals 0, and there's my x-intercept. If I plug x equals -4 in here, I get a y of 0, and there's my x-intercept. So the whole graph is moving over to the left 4 units, right? And again, maybe if we just summarize this with a slightly different example, if I were to take out my calculator and I were to graph y equals x squared, x minus 3 squared, x plus 2 squared, here's what I would see on my calculator. Right? Here's the original x squared, here's x minus 3 squared, and then here's x plus 2 squared. So this is interesting. It's kind of backwards. It's when I subtract 3, I actually move to the right, and when I add, I actually move to the left. So we can generalize that, right? We can say if I subtract h inside the function, that's going to shift me to the right. And if I add, that's going to shift me to the left. All right, now again, what I ultimately am trying to get to here is developing my tools of analysis, right? So I don't really want to plot a lot of points. What I want to do is, sketch a known curve. All right, so let me switch to my little drawing tool here. So this says graph the function f of x equals x plus 3 squared minus 5. So the main thing I want to think about is I'm starting with the basic function y equals x squared. And if I think back to the prior section, 3.4, that basic function y equals x squared, I'm going to do the best I can here, looks roughly something like this. Looks like that parabola. That's not the prettiest looking parabola, right? But you get the idea. And in particular, I'm going to focus on that x-intercept. That helps me visually kind of like grab a point and move the graph. Now, in orders of operations, I'm always going to work inside parentheses first, right? So the next thing that I'm going to do as I sketch this graph, I'm going to think of graphing y equals x plus 3 squared. Now what we just talked about was when we add or subtract inside the function, that's a horizontal shift left or right. And because I'm adding 3, that's actually going to be a shift to the left. So I'm going to go 1, 2, 3 units to the left, and there's my new x-intercept, and I'm going to do my best to kind of sketch my parabola from there. So there's the second step, right, of my rough sketch of my parabola. All right, and then the final thing that I'm going to look at is I'm going to look at subtracting 5. So I have the graph that we just sketched when we moved it to the left 3 units, and now I'm going to subtract 5 from it. Now remember, what we talked about from the prior slides is when I add or subtract a number outside the function, that's a vertical shift, up or down, right? And when I subtract, that's moving the graph downward. So I've moved the graph to the left 3 units, and now I'm going to move it down 5. Okay, so I'm coming down 5 units here. So I have that x-intercept. I've moved to the left and I moved down. So here's my x-intercept is now not an x-intercept anymore, right? But I'm grabbing this point, moving it left, grabbing that point, moving it down, and then roughly, right, my parabola extends from there, right? And this is a decent rough sketch. Now, I could add some detail to this graph. I could find the y-intercept by plugging in x equals 0. If I plug x equals 0 in here, what do I get? I get 0 plus 3 squared. 3 squared is 9, minus 5 is 4. So technically the y-intercept is up here at 4. So I didn't do a very good job sketching that parabola, but I could add that detail, although I wasn't asked to add it. Something I want you to think about here. I wasn't asked for that detail. I just wanted a rough sketch. And I could also find the x-intercepts, right? I could set y equal to 0 and find the x-intercepts if I wanted to add that detail. I wasn't asked for that detail, but I could add it if I wanted to, right? So here's a quick rough sketch of this function. And again, this is the general idea in this section. I want to be able to use known shapes and then shift, right, or translate the graph horizontally or vertically as necessary. All right, so let's say I throw a quick little multiple choice question at you, right? I'm trying to match to this graph what the equation would be, right? So let's see, what I'm going to notice is this graph looks like the standard square function, like my parabola. It looks like it was moved to the left 1 unit and it was moved down 2 units. So which of these would move me to the left 1 unit? So remember, adding or subtracting inside the square moves me horizontally. So if I move to the left 1 unit, it's either this guy or this guy. So it's letter C or D. These would move me to the right. Then I need to move down 2 units, so that's the addition or subtraction outside the square function, and it would be the subtraction in this case. So this graph matches that equation in letter D. All right, now again, we're using our tools of analysis. We haven't used any graphing technology, and so I could check my work here, right? I mean, I could bring up my calculator. Let me turn it on. I'll go to the y equals screen, and I'll type in my letter D to just check my work. So I'm going to type in x plus 1. Let me close the parenthesis and do the square. And then I'm going to subtract 2. And so let me do a standard window. I'll do zoom 6, my standard window. And yeah, that matches the graph that I have there. The square function moved left 1 unit and down 2 units. Right? So again, we have graphing technology to help us. It's a wonderful tool, but we are also developing our tools of analysis here, right? Our quantitative reasoning. So what I'm going to want you to do is kind of blend the two together, right? Do the problem without the technology, and then take out your technology and check your work. All right, so the next objective in this section is for us to consider doing what we call compressions and stretches. So in that first piece, we were looking at horizontal and vertical shifts. Now we're looking at compressions and stretches. So the first thing we're going to consider is a vertical stretch. So let's suppose I take the graph y equals absolute value of x and I multiply it by 2. What does that do to the shape of the graph? So if we look at a table, what we would notice is if we take the original graph and we multiply the y value by 2, I'm doubling the size of every y value. 2 times 2 is 4, 2 times 1 is 2, 2 times 0 is still 0, 2 times 1 is 2, 2 times 2 is 4, and so visually what I'm actually doing is I'm taking each y value and I'm doubling it in size. So we're going to call that a vertical stretch. I'm stretching this graph vertically when I multiply by the number 2. Now the other concept is, what if I multiply by the number 1/2? Right? Well, obviously I'm cutting each y value in half. 2 times a half is 1. 1 times a half is a half. Right? 0 times a half is still 0. Right? So visually, we're taking each y value, we're cutting it in half. We're pulling the y values kind of downward in a sense. But we're not going to call this a shift down. This is what's called a compression. So we're kind of pushing the graph towards the x-axis. And in the prior example, we're kind of pulling the graph away from the x-axis. We're going to call that a vertical stretch and a vertical compression. So we can generalize that. We can say that if we take any function f of x and we multiply it on the outside by a number, if that number is bigger than 1, right down here, if the number is bigger than 1, it's a vertical stretch. Here was that example of a vertical stretch. And if the number is fraction, smaller than 1, it's a vertical compression, right? And there's that example of that vertical compression. All right, now in this slide, what we're going to talk about is a horizontal stretch or compression. And these are a little bit weird. They kind of work backwards from what you would think, right? So in this example, I've graphed y equals x squared. Right, here's my original y equals x squared graph right here. Y equals x squared. I've kind of zoomed into my window here. All right, and when I multiply inside the function, right, I want you to notice I'm multiplying the x value by a number. So here the multiplication is inside the function. I'm multiplying the x by a number. So that's what indicates to me a horizontal stretch or compression. Here I'm multiplying the x by a number. Right? As where our prior example, I was multiplying the y value, the f of x, by a number. So here I'm taking the y value, multiplying by a number. That's outside the function. I'm multiplying the y by a number. Right? And here I'm multiplying inside. I'm multiplying the x by a number. So that's how I can distinguish between a horizontal compression, multiply the x, and a vertical, I multiply the y. So again, this was a little bit weird, right? If I multiply by a number bigger than 1, what it actually does is compresses the graph. Look at this. Here's y equals 4x squared. So I'm taking the original graph and I'm pushing in horizontally. That's how we're going to interpret this. So if I take the original graph, I multiply the x by 4, I'm compressing, I'm pushing in a horizontal direction, okay? So again, let me just grab my marker real quick. Right, I'm taking this point on the graph and I'm pushing in horizontally. I'm taking this point on the graph, I'm pushing in horizontally. So what we're going to actually say is that when that number is bigger than 1, we compress it by a factor of 1 over 4. Right? So here you kind of see they say it's a compression by a factor of 1 over 4. So I'm taking this x value and I'm cutting it by a quarter. That's actually what's happening. And then when I multiply it by a number smaller than 1, I'm actually pulling on the graph horizontally. So if I take this x value, I'm actually doubling the x value when I multiply the x by a half. And that's how we're going to interpret this. Again, this is a little weird. It's kind of backwards, right? But that's actually what we're doing here. So here's my original. When I multiply inside by a fraction, it pulls outward on the graph. So we're going to say it's a horizontal compression when the number's bigger than 1. That was this example here, right? That was this example here. And then it's a stretch horizontally when the number's bigger than 1. Or, it's a stretch horizontally when the number is fractional. All right, so I wanted to explore this with you real quick with Desmos. This is actually kind of cool with Desmos. So here's a vertical stretch or compression, right? So again, it's vertical because the multiplying number is outside the function. So for now, what I did was I have that number being 1. So this is 1 times x cubed. This is your basic cube function. And then what I'm going to do is I'm going to make that number get big. So here's 1.1 x cubed, 1.2 x cubed, 1.3 x cubed. And notice as I multiply by a number bigger than 1, that graph stretches, right? Let me go back to 1. That graph stretches vertically. Right? So I'm pulling up on the graph vertically. And let me come back to 1. When I make the number fractional, it compresses. So the graph moves down. It compresses towards the x-axis. And you can see the graph compressing. Okay? Now, what I'm going to do then, I'm going to take that multiplying number and I'm going to put it inside the function. So what we just talked about was that when I multiply the x by the number, that's horizontal stretch or compression, right? So there's the original cube when the a value is 1. Now, when I make the number inside bigger, look what happens to the graph. It compresses horizontally. So the graph is moving in horizontally from the original. Right? Again, the graph's moving in this direction. It's moving in horizontally. It's being compressed horizontally, right? And then when I make the number fractional, it gets pulled out and it gets stretched, getting pulled in this direction, getting stretched horizontally. All right, so let's take a look at another quick example here just to summarize this again. This comes out of the textbook, right? So here's the graph y equals f of x. So they're not even telling me what the equation is. They're just saying here's the graph y equals f of x, no equation allowed, and they're plotting particular points on the graph. Notice here's a point, right, a local max. Here's an x value. Here's a local min, right? Here's an x-intercept, sorry. So I got x-intercepts on my graph. I got 1, 2, 3, 4 x-intercepts. I got 2 local maximums and a local min. So letter A here is trying to get you to see that this would be a vertical stretch or compression. So it's vertical because it's outside the function. Now it's going to be a stretch because it's a number bigger than 1. So I'm taking every y value and I'm doubling it in size. So I'm going to take this y value and I'm going to multiply by 2 and it's going to pull up. I'm going to take this y value, multiply by 2, it's going to get doubled, right? I'm going to take this y value, multiply by 2, it's going to become negative 2. It's going to get pulled downward, right? So I'm going to get a vertical stretch. So each of these y values get pulled up by a factor of 2. This gets pulled down by a factor of 2. And here's a vertical stretch to my graph. Now for letter B, I'm multiplying inside the function by a number. I'm multiplying the x by a number. So this is a horizontal stretch or compression. And again, this is always backwards of what you think, right? Because I'm multiplying by a number bigger than 1, it's actually compressing the graph by a factor of 1/3. So if I was moving the points in particular, I'm going to take this x value and I'm going to multiply by 1/3. I'm going to cut it by 1/3 and it's going to become pi over 6. I'm going to do the same thing here. I'm going to multiply this by 1/3. It's going to become 5 pi over 6. Right? This x value is going to get cut. This x value too, right? This x-intercept is going to get compressed horizontally by a factor of 1/3. And all the points get pushed in, compressed horizontally by a factor of 1/3. All right, so the last objective in this section is to graph using reflections about the x or the y-axis. So let's say I graph the function y equals negative x squared. What that's going to do is that's going to take my original parabola, and it's going to take the opposite of all of the y values. So if I take the opposite of this y value, it becomes negative. I take the opposite of this y value, it becomes negative, and I, in essence, reflect the graph over the x-axis. So anytime we multiply outside by a negative, that's a reflection over the x-axis. So we can generalize that, right? We can say when we take the original function f of x, we multiply it outside by -1, that reflects over the x-axis. All right, now let's talk about reflection over the y-axis, right? So in this case, what we're going to notice is I don't have the negative on the outside of the function. I have the negative on the inside, right? I'm multiplying the x by negative x. So if I replace the x of 4 by a negative, it becomes -4, and that's a reflection over the y-axis. If I replace this x of 1 with -1, it's a reflection over the y-axis. So again, when I take an x and replace it with negative of the x, it's a reflection over the y-axis. So in general, we can say for the basic function f of x, if I replace inside the function with negative x, that's going to reflect it over the y-axis. All right, so let's look at a couple examples real quick about similar to what you might do in the homework, or what you'd be expected to do in the homework. So let's suppose that the homework question says, sketch this function here, h of x equals the negative of x plus 1 cubed plus 2, right? And so the idea here is they're going to expect you to start with the basic function. So the basic function here is the cube functions. The cube function looks something kind of like that. There's my basic cube function. All right, now, so the next thing would be to say take the addition inside the cube. So let's say I look at x plus 1 quantity cubed. I didn't do a very good job there. So that's going to shift the graph to the left 1 unit. So I'm going to take this point, kind of on my graph, I'm going to move it to the left 1 unit, and I'm going to move the whole graph to the left 1 unit as well. So there's a rough sketch of x plus 1 cubed. All right, now following orders of operations, the next thing I would do is I would look at the negative outside, right? So I'm going to take this graph and I'm going to put a negative in front of it. So here's what I'm doing. I'm taking this y value and I'm taking the opposite of the y value, right? Notice I didn't put the x, I didn't put the negative inside the cube, right? I didn't put it in the x value. I put the negative outside the cube. So this is going to reflect it vertically over the x-axis. So I'm going to take this graph and I'm going to literally reflect it over the x-axis. And so it's going to look something like this, right? I'm going to take this graph, literally kind of flip it over the x-axis, and there's the reflection over the x-axis. Right, and then the last thing I'm going to do is add the 2 outside the cube, right? So this is going to be a vertical shift upward. So I'm going to take this prior graph and I'm going to shift it up 2 units. So here I was at -1. I'm going to shift it up to 2 units. There's kind of that point that I've been grabbing, and then I'm going to sketch the graph from there. Now again, remember, this is a rough sketch. I'm not finding any x-intercepts. I'm not finding any y-intercepts. I'm doing a rough sketch. I'm using the basic cube function, and I'm thinking how each piece of the equation affects that original graph. This is us, again, developing our tools of analysis. Now, obviously, I could take out my calculator and check my work, and I would want to do that. All right, so unfortunately, when I take out my calculator, all that stuff I drew erases, right? But you should have those in your notes. So let's plug this equation in. So I want to make sure this is the negative key, not a subtraction key. So I'm going to make sure down here in the bottom right of my calculator, I use the negative key. And I put a parenthesis x plus 1. And then I'm going to raise it. I'm going to use the caret key here, raise it to the power of 3, and then I'll add 2. So when I graph, I see that basic shape that we sketched on that last slide of our shifted version of our cubic. All right, so again, we're developing our tools of analysis, right? It's definitely good for us to use our technology to check our work, but we also want to be able to do this by hand to develop our tools of analysis. So let's take a look at one last example here. So this example would say something like, graph this function, and we're going to want to use our rules of shifting, right? Our transformation rules. So the first thing we're going to do is start with the basic root function. So there's our basic root function, and we're going to start with that. Right? And then we're going to work inside the function, inside the root. And the next thing we're going to do is replace x with x plus 1. Right? So what that does is that shifts my graph to the left 1 unit. Then the next thing I'm going to do is replace the x with a negative x so that I can get this subtraction, right? This minus x. So I replace x with negative x. That reflects the graph over the y-axis. So I'm going to take this graph, I'm going to reflect it over the y-axis when I do that. And then the last piece would be to add the 2 outside, and that's going to be a vertical shift upwards, and there's our final sketch. Right? Now again, I want to do all that by hand. I want to understand how the pieces of the equation connect to the graph, but I can check with my technology. All right, so I lied. That wasn't the last example. We'll do one more example here. So in this example, it's a little bit different, right? So the prior example, we were given the equation, and then we were producing the graph, right? And in this one, we're kind of going backwards. They're kind of giving us the things that would produce the graph and asking us to develop the equation. So let's say in this example that we're going to take the absolute value function, and the first thing they want us to do is shift left 2 units. So remember, if I shift left or right, that's an addition or subtraction inside the absolute value function. So if I'm going to go left, I'm going to have to add 2 inside the absolute value function. So I'm going to replace x with x plus 2, and that's what that new equation would look like. And there's that new graph in this kind of magenta purple color. And then I'm going to take that and I'm going to shift up 3 units. So remember, shifting up 3 units or down 3 units is an addition or subtraction outside the absolute value. So in this case, because I'm shifting up, I'm going to add 3 outside the absolute value, and then there's that green shape. So I've shifted left 2, I've shifted up 3, and there's my equation. And the last thing I'm being asked to do is reflect about the y-axis. Now remember, when I'm reflecting about the y-axis, I'm replacing x with negative x, right? So in that case, I'm going to replace x with negative x. So in my equation, I replace x with negative x, and then I reflect this green graph about the y-axis, and it is now this orange graph. Okay, this video is a little long because we had quite a bit of stuff to cover, but this is 3.5. And again, as I've mentioned a couple times, we have technology to do all this graphing for us. It's wonderful to have those tools, but we are also developing our tools of analysis. All the problems up to this point, we have been having conversations about tools of analysis, but we've ultimately had technology to be able to graph the equations. What I want to do in this example is let's just take a look at a particular graph, and suppose we don't know the equation of this function. So we're supposing we have the graph of some function f of x, right? We don't know the equation, and what I want to do is sketch the graph of each of the following. So I'm going to do a couple different parts here. And let's say part A, what we want to do is sketch the graph of f of x plus 2. Now everything we've talked about up to this point, right, we've talked about when we add or subtract outside a function, that's a vertical shift up or down. So for part A, what we're going to do is shift up 2 units. Now the way that I'm going to handle this, I don't have gridded graph paper, so I'm just going to kind of do a rough sketch here. I'm going to take all of those points of interest and move them up 2 units. So let's just kind of work in a left to right fashion here. If I look all the way over here to the far left, I have the point -4, -2. And if I'm shifting vertically up 2 units, I'm taking -4 as the x, and I'm taking the y value and shifting up 2 units. So that's going to take me to -4, 0. So there's that first point we've shifted up 2 units. I'm going to do the similar thing to the next ordered pair here, -2, -2. That's going to shift up vertically. I'm taking the y value at -2, shifting it up 2 units. Now I'm at -2, 0. Now another point of interest that I have here is actually the origin, even though it's not specifically labeled for me. So the y value there is 0. I'm going to shift that y value up 2 units. And there is that point. And then again, just working from left to right, the next point is at 2, 2. Again, I'm going to add 2 to the y value. So that's going to take me to 2, 4. And then I have another x-intercept here at, 3, 0. So at 3, 0, that's going to move up 2 units. And then last but not least, this point at -4, 4, -2 is going to move up 2 units. And then I'll just go ahead and connect the dots here and resketch my graph. Now again, without gridded graph paper, I'm being pseudo precise here, and we're just focusing on the concepts. So if this original graph is the graph of some equation, y equals f of x, then we have just shifted upwards to graph the equation of f of x plus 2. For part B, let's suppose we want to graph y equals f of x plus 2. And again, whenever I add or subtract inside a function, that is a horizontal shift. And in this case, because we've added 2 inside the function, we're going to shift left 2 units. So very similar to what we did in part A. I'm going to take all of those specific points of interest, move them left 2 units, and then resketch the graph. Now without any specific gridded graph paper, right, let's just kind of be somewhat precise, but let's not be too particular here. So that very first point, we have -4, -2, and I'm going to move that point to the left. So whenever I move horizontally, I'm affecting the x value. So I'm going to take -4, shift it left 2 units. So that's going to move me to -6. So let's say 3, 4, 5, 6. So I got -6, -2 now is where that new point is. And then I'm going to do the very similar approach for that next ordered pair. So I'm going to take the x value of -2, shift it left 2 units. So I'm really at -4, -2 for that next point. Again, last time in part A, I picked the origin. We're going to move that left 2 units. Again, the x value is 0 there. So I'm going to subtract 2 from that x value. It's going to take me to -2, 0. When I take this next ordered pair of 2, 2, I'm going to take the x value of 2, subtract 2. That's going to move me to x equals 0. And then I have that next ordered pair at 3, 0. 3 minus 2 is 1. That's going to move me here. And then that last ordered pair, the x value is 4. Subtract 2. That's going to take me to 2, -2. And then we just resketch our graph by connecting those points. Suppose part C says we want to sketch the graph of y equals -f of x. So again, whenever I have the negative outside the function, I'm really taking the opposite of the y value, the opposite of the f of x value. So this is a reflection over the x-axis. So I'm taking every y value and changing the sign of that y value. So again, let's move kind of left to right. If I look at this first ordered pair, the y value there is -2. I'm going to take the opposite of that value, and that's going to move me shift a reflection, sorry, not really a shift, it's a reflection up to +2. And then ditto for the next ordered pair, take the opposite of the y value, and that's going to move me up to -2 comma +2. When I look at the origin's neither positive nor negative, so it doesn't really go anywhere. It reflects over the x-axis, which keeps it on the x-axis. Then I have the point 2, 2. I'm going to take that y value of +2 and make it negative, change its sign. And then I have the point for -2, and it becomes 4, +2. And then again, let's connect all of those points and sketch that graph. And you know, I forgot this point here at 3, 0 stays at 3, 0. Letter D, let's take a look at graphing y equals 1/2 times f of x. Now, just like we've discussed prior, when I multiply the y value, right, the outside of the function by 1/2, right, I'm taking all the y values, multiplying by 1/2, I'm cutting them in half. We called this a vertical compression. So again, we're taking the y values and compressing them by a factor of 1/2. So I'm going to take each of these ordered pairs, I'm going to take the y value, and I'm going to cut in half, and I'm going to multiply by 1/2. Again, moving from left to right, I'm going to take the y value of -2, multiply by 1/2, which is the same thing as dividing by 2, and that's going to move me to -1 as a y value. Again, similarly, -2 comma -2, the y value is -1/2, multiply by 1/2. That's going to bring me up to -1. The origin, right, the y value is 0. 1/2 times 0 is still 0. The point of 2 comma 2, multiply the y by 1/2, and that's going to bring me to 2 comma 1. The next x-intercept of 3, 0 stays at 3, 0. And then 4, -2 moves to 4, -1. Reconnect the points, and there's the graph of 1/2 f of x. All right, so the last one we'll take a look at here, letter E. Let's say we want to sketch the graph of y equals f of 2x. Now, when I multiply the x value by a number, that is a horizontal stretch or compression, and just like we've talked about in prior pieces of our conversation, right? Whenever we affect the x value, it's always the opposite of the intuition. So whenever I had f of x plus 2 earlier in letter B, right, this shifted me to the left 2 units, right? And even though we're adding 2, you think that would move us to the right, it actually moves us to the left. And same thing's going to happen here. If we multiply by a number bigger than 1, we would think that it stretches horizontally, but it doesn't. It compresses horizontally. And just to point out to you why that's working that way, so let's talk about how, first of all, this compresses horizontally. And it compresses horizontally by the reciprocal by a factor of 1/2. So let's just take a look at that first x value, that first point over here. So let's just take a look at that first point over here, -4, -2. And if we think about this just kind of numerically, what we're doing is we're taking that x value and we're setting it equal to 2x, if you will, right? And so if I solve for x, what I'm really doing is taking half of -4, and that's why we get that compression being the kind of reciprocal or the opposite of your intuition. So if I sketch a quick rough coordinate grid, then what I'm doing is I'm taking -4, comma 2, that ordered pair there, and I'm taking half of -4. And that brings me to -2, comma -2. I take that next ordered pair, -2, comma -2, and I'm going to multiply the x value by 1/2. And of course, that's going to take me to -1 on my x-axis. 0 times 1/2 is still 0. And then the next ordered pair, x is 2. I multiply that by 1/2. That brings me to 1, comma 2. And then the point at 3, 0, I multiply that by 1/2, and that's going to take me to 1.5. And then 4, -2 brings me over to 2, -2, and there is my horizontally compressed version of y equals f of x. So just want to illustrate that letter E visually. So even though in that prior problem we didn't have a specific equation, let's suppose our equation was f of x equals, let's say, the square root of x. Just be as simple as possible. And what I want to graph is y equals f of 2x. And before I do that, I'm going to plot a specific point. Let's plot the point 4 comma f at 4. Now obviously when I plot that point, right, when I plug 4 into my function, square root of 4 is 2, and that's what it's plotting for me there, is 4 comma 2. Let's go ahead and label it 4 comma 2. So what I want to do now is I want to graph y equals f at 2x. And when I graph f at 2x, notice this point here has been pushed inward horizontally. Okay, so in other words, what I've done at this point is by compressing the graph horizontally, right, and kind of making the graph look taller, but what's really a horizontal compression of a factor of 1/2. This video is getting a little longer than I like these